I was told keep it to 20 minutes. I don't know if I can do that. The physical layer's got a lot of stuff to go through. But I'll try to go fast and yet at a good pace for you guys to keep up. So let's dive into the details. You heard a lot of overarching ideas, but this is what the physical layer has to do. So the simple plan for today is go through the organization. What does S-32 look like? I think you already saw a slide. Get the main architecture up there. Please take a picture of it when you have the chance. And then I'll go through some key features of that architecture and then go through the document status. The key features will be just very high level. You're going to hear a lot more details in the afternoon from the ad hoc chairs of S-32-2 and S-32-3 and S-32-4. So more than likely a lot of questions will happen in the afternoon. Okay, here's the organization. You probably saw this slide before. The left-hand side is basically how 32 is organized, and the colors of the architecture there on the right are meant to map some more detailed diagrams later on. But the top piece there is an uplink, and the bottom piece is a downlink, and the blue box in the center is a link layer. That link layer is basically the middle layer that was described earlier of management and protocols. So that's how we interface to that. This is a very high-level diagram. This is the detailed diagram. So go ahead, take a picture. It looks, okay, this is the updated one. Good, thank you, Daryl. This is split into two pieces. There's the upper half and the bottom half. And up on the top left, you can see uplink, and then a downlink in the middle there. And on the far left side, you can see a broadband PHY and a broadcast PHY. Those are meant to show the actual interfaces of what we're thinking for the PHY. So uplink is for the broadband, and it's typically is going to be unicast based IP. But there is the option to have an output broadcast version. Not sure if that's going to be used in the US, but ATSC is an international standard, so for emerging markets that might be a viable option. For the downlink, you can see the different parts, and what we'll basically go through this morning and the afternoon is each individual, doesn't reach, each individual piece, those functional blocks. So hopefully we won't bore you too badly. Okay, all cameras are down, all right. So let's get into it. Let's get to the key features. First thing that we're going to hit is forward error correction. And basically, there's two pieces here. There's an inner code and an outer code. Okay? And the inner code is an LDPC with two different code lengths. And there's two different structures, structure A and structure B. Structure A is on the top. It's your typical LDPC type of organization or matrix. You have your information in your parity check matrix. And each one there has a quasi-cyclic structure of parallel factor 360. And that applies to the code rates, or basically to the upper code rates of 6/15 through 13/15 for both code lengths, basically. Structure B is shown with all the pretty colors in the bottom right-hand corner. That's an additional structure, and it's mainly applied to the lower code rates, 2/15 to 5/15, basically. And then on the outer code, once you get out of this inner, is a selectable version, either as BCH or CRC. Again, what we're hearing from other groups is we want flexibility in choice, so that's what we're providing. Broadcasters want the ability to choose. Moving down the line, we're getting to some constellations, and one of the key points that ATSC3 offers is non-uniform constellations. There's both two-dimensional and one-dimensional, but the curve on the bottom left basically shows the amount of gain you get with a non-uniform constellation. And it depends. If you're using 16 QAM, you can get about 0.2 dB. But if you're using 1024 QAM, it can get up to 2 dB. So that's where a lot of gain comes in when you're comparing ATSC 1.0 to ATSC 3.0. A large portion of the gain improvement in performance is with the non-uniform constellations. And on the right-hand side are typical examples of what's offered. There's the 1024 QAM on the top and 16 QAM on the bottom. Now, how does that fit into the Shannon curve? Well, Shannon is for AWGN channels only, and we understand that AWGN channel does not apply to over-the-air. Typically, it's going to be relay channel. But all standards use this Shannon limit for comparison, so that's why I'm throwing it up here. What you see is the Shannon limit in blue and DVB-T2 in green, and then the black dots or stars are where a 53 lie, and then at the bottom, maybe bottom left-hand side, there's 3 black stars as well, just below the green lines. That's a 153. And all the little red dots that are in between, that's ATSC 3.0 today. As you can see, at the lower end of the SNR, we're very close to the Shannon limit, as are other standards, but we're still a little bit better. And as we get up into the SNR region, maybe 15 dB, 20, 25, and as we grow, we're hugging the Shannon limit closer and closer. And the reason for that, or a big reason for that, is the non-uniform constellations. And they're pairing with the LDPC codes. You'll be hearing more about this later this afternoon from S-32 presenter Lachlan Michael. So what's going on here? For the low code rates, it's basically on the bottom left. You have low capacity and very high robustness. And one of the key points I want to make out here is that the furthest left red point is around -6 dB C to N. -6. That's 4 times less power than noise can be an operating point. Or we can have an operating point at the very high end of around 30 dB, and it takes about, let's see, less than 50 megabits per second capacity rate at that region with a 6 megahertz channel. But it is also very efficient and has high capacity, but it is less robust because it takes 30 dB SNR in order to receive it. But this flexibility of choice is the main thing that we're coming out with. No longer are we tied into one operating point. Broadcasters have the ability to choose. Okay? One option that we're coming out with is time division multiplexing, which is well known in the industry, but an option to that is layered division multiplexing. And layered division multiplexing is, just like the first bullet says, it's a new transmission scheme that uses spectrum overlay to superimpose multiple physical layer data streams with different power levels. So this basically comes from CRC and ETRI, and I think Ian has used the analogy of a double-decker bus, but just think of, instead of a double-decker bus, you have a triple-decker and a four-decker kind of bus, and it just adds and adds and adds. And basically, if there's some kind of, there we go, animation onto the right, you can see layers being subtracted as you take them away and get to the raw feature, a raw layer of RF, and then they can be placed back on. Okay, next up, or a key feature is MyXO, and that basically means MISO or SIMO or also MyMO. The basic MyMO capacity gain, that chart's on the bottom right. No big real surprise here. You're going to get a large MyMO gain with high SNR, so we want to make that offering to broadcasters. It's also applied to lower SNR regions, but not as much gain. So people always focus on the high SNR region, but it doesn't mean that there's no gain for low SNR, it's just much less. Typical equations for MyMO, basically of a channel MyMO, is shown on the top right. But basically, we're looking for SFN operations and antenna diversity options and a wide range of operating points here. So Be looking for MyMO in ATSC3 as well. Okay, a little word about network flexibility. So if I'm looking at a single big stick, you'll have a radio horizon like as shown there, okay? One big circle. All right, it's not true to form, but let's just have this as an example. One way to build out a network with SFN, for example, is let's have 3 towers added, and they're also omnidirectional, so they go all over, even inside the circle and outside, and basically that gets spillover into adjacent markets. Okay, well, is that a best way to go, or is there a better way to think about this? Okay, if we change the antenna pattern, let's leave the single big stick up there and start adding different SFNs that point inward. That gives the ability to have higher chance of reception in your market area today. So there's a key point that I'm trying to strive here. There's a difference between coverage area and service area. Service area means you can actually get indoor penetration and deep inside parking garages, that kind of thing. To do that, it's not necessarily bumping up the power of your main big stick and just broadcasting more power into it and thinking it will reach indoors. That's not the case. Reception indoors and reception for mobile devices is all about received signal strength, okay? And received signal strength is basically a part of the antenna function, number one, and basically angle of arrival. So even in smartphones today, you'll have 2 antennas, and they're orthogonal to each other because they have found out that a different path of arrival might have a better chance of reception than the direct beam. So that's where this SFN comes together. If you have different angles of arrival into your market, the odds of reception are much higher. Now, this doesn't mean that you're going to get bombarded with a lot of signal level in the center there where it's kind of around the main tower, where, well, I think it's like brown color, I guess. That's not necessarily the case. It just means that there's more odds of reception of higher. The probability of reception is higher. And there's no spillover into adjacent markets. That might be advantageous. So greater indoor penetration in the center. Okay, if there's more power, does that mean you have problems with echo tolerances? Not likely with OFDM. OFDM has a guard interval, and what is a guard interval? It's basically a piece of the OFDM symbol copied and pasted to the beginning. So any echoes that fall within that guard interval will be automatically canceled. It's a simple function. There's no real long equalizer like there is in ATSC 1.0. And even if an echo falls out of the guard interval, it doesn't mean that it loses reception. It just means that there is more degradation in the receiver to tolerate. So an example of the guard intervals is basically in this chart. There's 12 of them. And basically it does vary on FFT size as to what applies. But if we have a look at the bottom left-hand column under 6 megahertz channel, you'll see 703.7 microseconds as an available length for 32K FFT. Typical operating, I'll say it this way. A natural occurring echo is basically the main point we're trying to solve. And I think we've heard that the maximum length of a recurring echo is seen in San Francisco, which is around 104 microseconds. So the fact that we go out to 700 means there's a lot more flexibility. Why would we want to go out that high? Well, with an SFN, you have time of arrival. So to compensate for the time of arrival, in addition to the natural occurring echoes, you want to have that choice of long guard intervals. Okay? All right. This is what came out on May 6th for the candidate standard. It's a Bootstrap. It's the symbols in blue that you see there. This Bootstrap is very, very robust. it typically performs lower than minus 6 dB SNR, typically. And that's not just for that's not AWGN channel, that's relay, that's TU6. That's a lot of pedestrian indoor, pedestrian outdoor type of channels, which are true over-the-air type channels. So we've been studying this for many months, and this Bootstrap looks to be the way to synchronize everything into one starting point for the physical layer, and that's why it's at the bottom of the architecture document, architecture structure. It's the starting point, and this Bootstrap will do that. It has 22 signaling bits, and it signals the sampling frequency, the channel bandwidth, an EAS signal, preamble selections, time to next similar frame, and some other stuff for the next following preamble. So it's just the basic starting point, and it's that key piece of a priori information that is given to the receivers. And it's very robust. So that's the starting point for us. What does it really do? What does it look like? It's a Zadov-Chu sequence, starting with various roots, and it's modulated with a PN sequence with certain seeds. So we can signal major, minor versions of the standard with this major and minor piece here, basically the Zadov-Chu root and the PN sequence seed. And it serves as a synchronization detection to all receivers with this known sequence. And the parameter selection is conveyed through the initial synchronization, followed by the other symbols. Okay. And we get to hear bagpipes. Okay. The Bootstrap and the time domain. Yeah, how about that? You know, all the Scottish people raise their arms. Okay. In the time domain, it's basically a 2048-point FFT, and we're going to cyclically shift or frequency shift that in the time domain to have that added version of robustness. And what you saw in the previous slide is a single, up in the power spectrum chart there in the middle of the page, a flat frequency spectrum that shows basically 5 megahertz width. Well, that is inverse FFT, and it's a time domain, and we're taking pieces of that 2048-point FFT and shifting them around into a CAB structure there in the top right and the BCA structure in the middle right. That adds the robustness, and it adds a little bit of degree of synchronization for the receiver to understand what is a starting point, when's an end point, and to have a robust synchronization. So there's the Bootstrap in frequency and time domain. Channel bonding is another option. I'm almost done here. I think I'm running late. But basically, the concept of channel bonding is to mix VHF and UHF channels. The ability to put things together and offer a choice for those on VHF channels to do mobile, a chance for the people on UHF to put off non-real-time service into a VHF channel if they so desire. And it also adds different channel bandwidths that are possible to sum up. So you can have options of 6, 7, 8, as shown there, 12, 13, 15, 16 megahertz options. Okay, working JAF status, there's basically 3 parts that we're coming out with. The system discovery and signaling document, that's out, check, done. Well, not check, done, it's in candidate standard, so we're having inputs to that. Next up is the physical layer standard with parts. We're going to get that out this summer, and then the return channel is coming after that. So in summary, basically the 3.0 system standard enables system options for broadcasting, not just the system parameter options. It's totally different, totally open to new things. It has high robustness, spectrally efficient operating points, flexible configurations and operating modes with a large SNR range, robust synchronization with the Bootstrap that has basic system parameters, channel bonding options, flexible functions for optimization per broadcaster if they want to do MyMO, SFNs, whatever they want. And the starting point of this physical layer is the link at the bottom, which is the candidate standard. I think that's it. Oops. That might be it.